Okay, YouTube, this video we're going to be looking at kind of a preamble to completing the square, but just kind of looking at how perfect square trinomials would be a benefit to us when trying to solve some sort of quadratic expression. So recall that what we mean by a perfect square trinomial, we're talking about the trinomial that results when you actually square something like this out, a binomial. And so for something like this, remember that we would get a squared, okay, so we get a square up front. We would get plus an AB plus another AB when we FOIL this out, and then we would get plus a B squared. So I think the key to recognizing a perfect square trinomial is to recognize that the outer two terms here are perfect squares, and also that when you look at this A and this B here, at least these two values that you put in this parentheses here, the middle term is always 2 of whatever A times B acquires. So when we look at these three here, what I'd like to do is just solve these equations, but do it using this kind of completing the square approach, which is to take something that is a perfect square trinomial and just write it as the square of a binomial. The benefit to doing so would be that we could just take the square root of this and the square would go away. So looking at all three of these expressions, what I want to point out is that all three of them, as a matter of fact, are perfect square trinomials, or at least right off the bat I instantly recognize that in my trinomial here that the outer two terms are squares. Okay, so when we factor a perfect square trinomial, it factors down into the square of a binomial. And so what I would say is, well, my A value, okay, this A here, that would be what I would square to get my first term. So what I would square to get an x squared is just an x. And then this B value here, when I factor this, would be whatever I squared to get this last term right here, which my last term is 16, I would square a 4 to get this. And because, okay, I wrote down the pattern here for A plus B squared, if it was A minus B times A minus B, then we would have gotten A squared still in the front, okay, but we would have got a minus 2AB and still a positive B squared, because when you take a negative B times a negative B, you get a positive B squared. But the idea here is this middle sign right here, whether it be a positive or a negative, should match the sign in your factored form. So because I have a negative 8 as my middle term here, I would say that this is a negative here in the middle. And just to check this also, if I took 2 times x times negative 4, well, negative 4 times x is negative 4x, and when you double that, you certainly get negative 8. So the importance of this, first of all, is that you recognize that this is a perfect square trinomial, and second of all, that it indeed factors down into something like this. Now, the benefit to factoring it would be that, again, now I could take the square root of both sides. And actually, I'm going to rewrite this. So we get x minus 4 squared equals 25. And I'll show my work on this line just to kind of distinguish between the steps. But what we do, once we do this, of course we would get just x minus 4 on the left. And in this case, we get a square root of 25 on the right, which it doesn't always happen, but in this case, comes out to be a nice integer. So we get plus or minus 5, and it is imperative that we remember the plus or minus. When we take the square root of anything, that we remember a plus or minus, because recall that 5 squared equals 25, okay? But so does negative 5 squared. That also equals a positive 25. So we have to account for both of those roots. And so the last thing we're going to do here is just add 4 to both sides. And so what we end up with is essentially x equals 4 plus or minus 5. Now in this case, we could actually simplify this, and that's precisely what I want to do. I want to say that x is 4 plus 5, and that x is 4 minus 5. And so in either instance here, we get a whole number solution. 4 plus 5 is going to give us 9, and I'll put a box around this. And 4 minus 5 would give us negative 1. Now, I'm also going to put a box around this one right here, because this is an acceptable answer. But if you can simplify it, then we're certainly going to simplify it if at all possible here. So what I'm going to do, actually, before we move on to the next couple of examples here, is recall that when you find the solutions, or the zeros of a quadratic equation, what you're really finding are the x-intercepts of the graph. And so what I want to do is I want to go show you in your calculator here, and you should graph these when you're done, that you get these x-intercepts. And so before I graph it, the first thing we want to do is make sure that this would be set equal to 0 by subtracting the 25 over to the left side, but 16 minus 25 actually gives us a negative 9. So what I'm going to place into my y equals here is y equals x squared, okay, or x to the power of 2, minus 8x minus 9. And when I go graph this, what I anticipate is that we get an intercept here at negative 1 on our x-axis, and we also get an x-intercept at positive 9. So very good to verify these things as you work through it. So let's kind of keep this pattern going here, at least for this whole first set of problems here. I, on purpose, am providing you with a perfect square trinomial, which always means that we can write it as the square of a binomial. So for instance here, I would say, well, what could I square to get r squared? I would square an r. What could I square to get a 25? Well, I could square not a 25, a 5. And because my middle term is a negative, I'd put a negative here. And so with this, again, what we're going to do is we're going to take the square root here of both sides. So we take the square root of the left and the square root of the right. In this case, on the left, we get r minus 5. And on the right here, we get plus or minus 1. So again, this one works out quite beautifully. I mean beautifully because we get nice integer values. It's not always going to happen as we see in this next problem, but we get r is equal to 5 plus 1, which is 6, and 5 minus 1, which is 4. So these are our two quadratic zeros here. And again, what I want to show you is if we were to go graph this, and also when you graph it, we have to have it equal to 0 here. Let me clear this out, but we'll put in x squared minus 10x, since we're dealing with just x's on our graphing calculators, minus 10x. I want you to try the same thing, please. If I were to subtract 1 from my 25 to set it equal to 0, it would be a plus 24. And so what I end up with is this graph right here that we anticipate would cross at a positive 4 and a positive 6, and we can clearly see that on our graph. Now let's look at this last example here. This one actually carries a little bit more substance. I certainly do recognize that 4w squared is a perfect square of 2w, and that 1 squared is a perfect square of 1, and because my middle term here was positive, I'll put a plus here. So just like we've done in the first two here, we're just going to rewrite this perfect square trinomial as a square of a binomial and then carry out our square root on both sides. So if I take the square root of both sides here, we get 2w plus 1 is equal to plus or minus the square root of 75. Now, from here on through the rest of the problem, what I want to point out to everybody is that we are perfectly capable of getting w by itself by subtracting the 1 first and then dividing everything by 2. But it's going to involve a lot of simplifying, which is kind of a drawback to using this technique. So let's go ahead and make sure that we don't make any mistakes here. I'm going to go ahead and I'm going to subtract 1 from both sides. So I would get 2w is equal to negative 1 plus or minus the square root of 75. And I'm also going to divide both sides by 2, which means we have to divide everybody by 2. So we get our two answers here, and they are negative 1 plus the square root of 75 over 2, and negative 1 minus the square root of 75 over 2. So in terms of simplifying here, this is a 7 in here, I recognize that the square root of 75 is really the same thing as, and we want to reduce this if we can, 25 times 3. So because this is true, let's rewrite this again a couple times. Rewriting, that's just part of math class, I guess, sometimes. 25 times 3 here, we're going to take the square root of 25 and stash that out in front. So my two solutions here happen to be negative 1 plus or minus 5 root 3 over 2. Now, one thing that I want to have us do on this one is actually carry this out on our calculator and get a couple of values here. So what I'm going to do is I'm just going to slide this over here. I'll go to quit, and we'll go out to the main page. We're going to type in parentheses, negative 1 plus, okay, and I'm just going to use the square root of 75 for right now. Square root of 75. Now I need two end parentheses, one to end my square root and the other one to end my numerator. We were going to divide this all by 2, and I'll hit enter here. And the next thing I want to do also is just hit second enter on these TI calculators. It just pulls up the last thing you typed in. The benefit of doing this is that we can just go back and change your addition relationship here to a subtraction relationship. So keep an eye on these two decimals, about 3.83 and negative 4.83. I'm going to write these down, negative 4.83 and about 3.83. And when you see this double squiggly here, it just means approximately equal to. You could also just write ish at the end of this. So it's about 3.83-ish. I think the idea, though, is, again, I want to go graph this on my graphing calculator and show that these are actually my x-intercepts. So if I were to set this equal to 0, that would involve subtracting 75 back over there. That's going to make this a negative 74. So to graph this, we would say 4x squared plus 4x, and we would get minus 74. And go take a look at this graph here. What we're looking for is that our graph does indeed cross. Let's see here, 1, 2, 3, 4. Here's negative 4. Negative 5 is just on the other side of this. You can see that it crosses between negative 4 and negative 5. And it also crosses at 3.83, which is somewhere between 3 and 4 here. You can see 1, 2, 3, right between 3 and 4, but really close to 4, we're getting this. And so I have to ask the question here, would I prefer to have these exact values, or would I prefer to have the approximate values? And they're both meaningful, okay? But I would say that these approximate values, they are valuable when graphing, okay? Or when we're solving an application problem. And these are valuable when we want solutions, okay? So we just want this right here. So factor your perfect square trinomial into a square of a binomial, and then we could just solve these using square roots. Cheers.